going to be talking today about the future of patient matching. I really should have called the presentation the near future, because everything we're going to talk about are things that are coming down the pike now that can be implemented in providers' locations today. We're going to compare and contrast the older matching technologies we've been using and then see how they compare against the newer technologies, really the future of patient matching. And we will then have a good idea how we can do better patient matching with a combination of all the technologies available to us. Universal patient IDs, old probabilistic algorithms, and the newer AI fancy machine learning stuff. It's all in here, and it should be interesting. So bear with me. It's a lot of information, and I will do my best to keep it fairly understandable. Cross my fingers. I've been doing this literally for 30 years. Anything in the healthcare market, plus financial market, and also the intelligence community. So hopefully some of that information and experience will be valuable to you today. It's a lot of data, I know, a lot of information. So let's dive into it and see you at the end. Thank you. My formal name is James, my nickname is Jim, and that's my preferred name as well. I always draw that distinction on these patient identity topics to illustrate the points. I'm the co-founder of Medarcus and chief of strategy for the company. I'm focused on applied research and publications on health IT matters. I'm the current co-chair of the California HIM Association Health Information Integrity Committee, where I'm leading the team on a forthcoming effort to publish an EMPI toolkit. And this presentation will discuss the path from 1918 when SoundX was first patented, and we'll go through the use of artificial intelligence today. Our objectives for the presentation will be to review the history of patient matching techniques, and we'll go back the full century and discuss everything that's happened that's relevant to what we do in healthcare today. We will explore how patient matching works. We will examine the applicability of common matching approaches, with the idea that we want to understand the kind of duplicates that each approach was designed to identify. Then we will move to the current matching approaches that are used in healthcare today. Every provider has hidden duplicates, and these duplicates, as we'll learn, are the result of the limitations of matching algorithms that we're currently using. There's going to be a strong recommendation that providers use a range of matching approaches, not just one, because as an industry, we are most interested in patient safety, and as you'll learn, every matching approach has its value and limitations. So these approaches are best used in concert with each other, not exclusive of each other. And then we'll start to focus on the future of patient matching, and I'm excited to share it with you. Probably my favorite part of the presentation will be towards the end, which is how we can use these technologies, old and new, to prevent errors from going into the MPIs in the first place. It's a lot smarter to stop the errors from going in than it is to clean them later. We'll close out the presentation by looking at how the modern matching technologies can solve other very difficult problems in healthcare IT today. So that's a really big agenda for an hour. Let's get going so we can fit it all in. Let's go. My grandmother was born in 1919, God rest her soul. That was just 1 year after the first patent was filed for a matching system. The patent described SoundX as a system to translate the phonetic sounds of names into a code and that code can be compared so minor spelling variations will not impact the match. Thus, this was truly the first matching system. Patient matching is known as record linkage. In other industries, deduplication processes are required with some frequency, and that should sound familiar to us in healthcare. For clarity's sake, let's define what we mean by overlap analysis versus deduplication. Deduplication is where one data source has two or more records for the same person or entity, two patient records in the MPI that belong to the same patient. An overlap analysis is where the same patient has two records but in two different systems, and we're trying to link those two records together. Whereas with deduplication, we're trying to merge those records. Very different. We've all seen overlap analysis before, I'm sure, due to the common merger and acquisition process that's in our healthcare industry, or when smaller practices are acquired by a hospital. And you can see from this representative webpage from Becker's Hospital Review that lists some of the mergers from 2020. And this is the same year upon year in our industry. Most of us have probably been part of a patient matching project where we looked for duplicates and we remediated those that we found that matched, where the match was based on some sort of set criteria. And if you think about it, patient search is also patient matching, where search has the same process as matching, but usually just less fields. Search, as it turns out, is a fundamental driver of innovation for healthcare, at least recently. Medical records are stored in an EHR, Electronic Healthcare Record System, or sometimes referred to as an EMR, Electronic Medical Record System. The Master Patient Index, MPI, is the portion of the EHR that contains patient demographic data. It's this patient demographics that are used for patient lookup and patient search, as well as for patient matching. So let's do a little bit deeper dive now on what process of patient matching actually is. To find a potential match for every record, we need to compare every record to every other record in the EHR, going record by record, cataloging suspected duplicates, and when we find potential matches, we set those aside for review by the HIM professionals. All the records in the MPI. Every time we find a match, we put it in the suspected match queue. Overlap analysis is slightly different than duplicate analysis. With duplicate analysis, we are comparing every record against every other record in one MPI. With overlap analysis, we are comparing every record in one MPI against every record in a second MPI. The output from overlap are a list of records that might be linked together. That is, patients that are shared between two providers, for example. The important part for this presentation is to recognize that it's the same exact technology that does duplicate record detection and analysis as it is the same software for overlap analysis. How patient records are compared is the root of the differences in the different matching approaches, more or less. Let's take a look. The initial idea of record linkage goes all the way back to 1946, when an article was published called Record Linkage. And then in 1959, the concept of probabilistic matching took hold. That was the foundation of an algorithm called Flegge-Sunter, named after the inventors, that is the root of what we use in healthcare today. And there was a long period between then and the 80s when artificial intelligence became popular, which is when I got my master's degree in computer science. We started to learn how to use neural networks to do classifications, that is, record matching. And that takes us to the 1990s. While I was working at the National Security Agency, I worked directly for a chief scientist who invented a very unique pattern matching approach. and that has direct applicability to matching patient records. And it's been an exciting 2 or 3 years for other developments as well. We've seen the industry grow by the inclusion of biometric devices for patient identification. We've seen using external data for referential integrity, and then pattern matching that I mentioned earlier. And now a brand new category of algorithms are starting to become popular in healthcare. And I'm going to call those algorithms soft biometrics. It's a term I coined last year to cover a bunch of solutions that helps us identify patients. You will hear me use the term algorithm quite a bit in this presentation. So I should probably define it for you, since most of the audience listening are probably not computer scientists or data scientists. I hope not anyway. Nonetheless, let's talk about what an algorithm is. In the most simplest of ways, you could think of an algorithm like a recipe. A recipe gives you instructions on how to make a pie using ingredients in your oven, for example. In a similar manner, you can think of a computer like an oven, and the algorithm is like the recipe that gives instructions to the computer on how to make something out of the data. In our case, we're trying to find duplicate records. That's what our matching algorithms do. And just as with recipes, there are many algorithms. Different recipes have different ingredients, resulting in different flavors, different textures, and different tastes. And algorithms are the exact same way. Patient matching is performed by a computer program, and each computer program has a matching algorithm inside it. And different matching computer programs produce different results, just like with pies. Pumpkin pies and apple pies are both delicious, but we used 2 very different recipes to make 2 very different pies. And the same with patient matching. We often will get different results from different matching algorithms. These matching recipes or algorithms are all very different in their approach. Older style matching will use things like phonetic names. Very simple matching will use deterministic approaches. And then the most sophisticated algorithm in place in most organizations is a probabilistic algorithm. Recent matching approaches include things like biometrics, using hardware and software to do patient identification. And then there's something called referential matching, which is useful in some instances, but not all. And that kind of takes us to what I'm calling the near future. Today, tomorrow, just around the corner, we're looking at using machine learning or artificial intelligence to do patient matching. And we'll discuss pattern matching, which is a really interesting way to get fault tolerance in both search and patient matching. And the last of the newer types of approaches is something I call soft biometrics. But I can almost guarantee you everyone who's listening to this today has used an algorithm that I'm going to describe, just not in healthcare. Yet. SoundX is probably the most widely known and most widely used phonetic algorithm. It's not really a matching algorithm for the entire medical record because it only matches the names, first and last name, or maybe even middle name. But I mention SoundX here because a lot of organizations use it on a daily basis to find patients in their EHR. Even the US Census still uses SoundX because it matches data a century ago. For example, the names Stewart and Stewart, S-T-E-W-A-R, versus S-T-U-A-R-T have the exact same SoundX code, S363. And that's great if you have 2 different Stewarts in the MPI that are the same patient. But keep in mind, this is only useful for name matching. And as we talk about later, names are not the most unique patient data that we have to match on. There are several other phonetic algorithms that are useful too, but they're less commonly used. Algorithms like Metaphone, NYSIIS, and Bider-Morse, which takes into account the language of origin of the name that's being phonetically coded. The next class of algorithms are called deterministic, and they are probably the most common ways to match records. And it's a very simple reason. It's because deterministic algorithms are simple to create. So most IT departments, or even those users that are experienced with report writing tools, can implement a deterministic algorithm. And what's so great about deterministic algorithms is that they're very easy for humans to understand. It's literally just like a recipe, actually. Typical logic would be if 3 out of 5 fields are the same, then the patient's match, or 2 out of 3 fields. And it's a very simplistic way, but effective, for data that's relatively clean. That is, they're fairly obvious duplicates. The code sample I have on the right is just a mock-up, but it gives an illustration of the kind of logic that a deterministic algorithm would have. And because we can read it, it's in human readable form, you get a sense for how easy it would be to write it up in a report or have an IT department just do a simple little program to do some deterministic matching. Thus, it's done quite a bit in hospitals. Now, the limitations of deterministic algorithms are fairly substantial, because generally we're looking for exact equivalence in the field. We don't have the power to look for things that are similar. It really has to be exact. And that's a problem because most EHR systems do not have what's called normalized data. That means the data is standardized. So if your data is not standardized, say everything in capitals, or everything is formatted exactly the same, there's going to be a substantial amount of data that should match, but doesn't because the data is not truly exact. Capital A is not the same as lowercase a for computers. O'(H) is not the same as O'(H), so we're going to miss the O'Hares, for example. In practice, deterministic algorithms miss names that really have simple errors in them because they're not that powerful. So it misses examples where the letters might be transposed, or there's missing or extra characters in a name. And any kind of abbreviation at all will absolutely not match full spelling, Main Street, or Main ST, for example. One of the improvements that can be made is to bring in the concept of a string distance. That is, to see how different two names are, and then use that score as a measure of similarity. In the first example, we're just going to transpose 2 characters, the E and the S. The next example, we're going to delete or add the R to make the names match. And then the last example, we will add REET and remove the period, so one Main Street matches in both examples. And string distances are important to understand because some older EHRs actually use a string distancing algorithm as their main way to determine patient matches. Let's just leave it to say that it's not a bad technique, but it's not sophisticated enough to do the job by itself. In the category of current matching approaches, there are 3 algorithm classes that I think are worth mentioning today to get a sense for the current state of patient matching. The first one being probabilistic algorithms. This class of algorithms has been around since the late 60s, so it's fairly well understood, and there's a lot of examples of it in use. Inside EHR systems, vendor software packages, and so forth. It's readily available. Another contemporaneous approach for patient identification, not necessarily finding patient duplicates, is using biometric hardware to measure characteristics of a patient to compare it against the data that's already stored. And another interesting idea that's in common use today, although it's not entirely practical, but it's filling in patient records with information from external data sources. It's not applicable for all patient types, like children or undocumented workers, but it does have a place in solutions. So let's talk a little bit deeper about probabilistic matching. It's probably the most sophisticated algorithm class in use today, on a widespread basis anyway, and AHIMA defines it as such. So a lot of interest has been placed in probabilistic algorithms over the past decade or so. The algorithms we will talk about in the future section will begin to displace probabilistic algorithms because they're more powerful, but it's still early on in the adoption of these more sophisticated techniques, like artificial intelligence. Probabilistic algorithms work based on how common a name is. For example, I picked a very uncommon name from a list of names that the US Census publishes, FEYR, F-E-Y-R-E-R. And if 2 records have that same last name, the probability of a match is pretty high, as very few records in the MPI have that same name. But if a patient's first name is James, it's the most common name in the USA. So if two records have that first same name, the probability of those two record matching are very low, because there's probably many records that have the first name James. That is the essence of how probabilistic algorithms work. There's both a positive and negative influence on the records matching, and this is done on a field-by-field basis. The positive and negative indicators for probabilistic algorithms was groundbreaking at the time. It's almost like the yin and yang of matching. Records match for some reason, and other reasons are things we might consider that don't match. So weighing these two probabilities is what it's all about. The most common probabilistic algorithm is called Filegi-Sunter, and in its simplest description, it just computes a ratio of how unique the values are versus how common they are. And that ratio is the match score for that pair of data. And when you combine all the values for the fields together, it should rise above a certain threshold for the entire record to be considered a match. That threshold is configurable, so there's often a lot of work in the beginning of these projects to tune the algorithm thresholds properly. The threshold is also probably one of the biggest weaknesses of this algorithm too, and it's a reason why we often have false negative. That means missed matches. Because some records are near matches, but not good enough to pass a threshold, but they're still duplicates. All scoring algorithms have this potential weakness, but it's pretty significant. And this is why artificial intelligence and pattern matching typically are more powerful, because they don't have this flaw. The success and failure of these score-based algorithms are specifically determined by how good they're tuned. And that's always done by a human, done infrequently, and it's very likely not to be perfect. The next contemporaneous solution are biometric systems. And these hardware devices measure the characteristics of human beings, like the patterns of the blood vessels on the back of your eyeball, or your fingerprint, or even the sound of my voice. That is also a biometric signature. These solutions require both hardware and software to verify patients, and they're big projects with significant maintenance cost as well. The solutions tend to be very expensive when compared to software-only solutions, and they're actually much bigger, more complex projects because the devices have to be installed and maintained in the registration environments. Some patients and others have expressed concern about the sterility of the devices after use. That's especially sensitive now in times of COVID. And there are a lot of reports about the invasiveness some patients feel when they're registering. So some of these issues might impact patient satisfaction, for example, for some providers. So there is hesitation for using purely biometric devices. We do have to observe that many smartphones now use fingerprints for logins. But probably the biggest reason to be cautious or not overly optimistic about this particular class of solution is that it's really just forward-looking. It does nothing to clean up your backlog of duplicate data already. It's a big expense, and it doesn't really clean your data. It just prevents other errors from occurring in the future. The patient safety risk for duplicates still exists. Another current solution that's available today is using external data sources to fill in missing data. This is really just about collating data sources together. And the downside is that it only works with those patient populations that have public data profiles. So undocumented workers, children, others that don't have public information will not necessarily benefit from this approach. This is the kind of solution, external data referencing, that is really just a part of a solution, not the sole solution, just a small part of a bigger system. What is the future or near future of pattern matching? Now that we understand where we've been, we have a really good directional indicator of where we need to go. And just like with the older algorithms like SoundX or string distancing, even these modern techniques are really useful putting them into the older systems. as well as using them for standalone matching approaches in and of themselves. Machine learning is a fantastic way to set the weights and score thresholds for probabilistic algorithms. That tends to be the state of the art in today's matching, because artificial intelligence does it better than humans. Even more interesting is that machine learning gives us additional capabilities that the older algorithms simply cannot do. For example, it clusters patient records together, not just pairs them. Important distinction that makes modern algorithms much more practical than older ones. Pattern matching is probably my favorite. It's one of the latest advances in healthcare, but it's based on work that I did a long time ago at NSA, and many others have done since. It's not a new idea, but it is new to the healthcare industry. So we'll talk about that and how pattern matching works for medical records. And finally, there's soft biometrics, to really cover a class of algorithms that are things we have today, but we're just not using in healthcare, so we'll discuss. Now, one of our newest approaches, machine learning, actually goes back a half a century ago, when a researcher at IBM discovered that if he memorized the checkerboard of all the wins and losses from every position, that would give him a way to estimate the best way to go with every move. And this kind of rote learning that he programmed into the computer was the first example of machine learning. We've come a long way since then. But machine learning essentially now involves modeling the brain in what's called a neural network. And these neural networks, or brain models, need to be trained, and that happens either as a supervised or unsupervised function. Supervised meaning we give it examples of what the correct answer is, and unsupervised meaning it just figures it out on its own, just like us humans. It's kind of scary, actually. The real essence of these types of algorithms are that they're classifiers, and it's what humans really are good at. Is that a friend or is that a foe? For example, this photo of a hose in my walking path at home kind of looks like a snake sunbathing. And it's our brain that instantaneously deciphers, no, that's not anything I need to worry about, that's just a hose. But we figure that out before we even know we're doing it. That's what machine learning really does. The power of our brain and neural networks to make that classification quickly. And these neural network models were taken input, say 2 patient medical records, and determine if they match or if they do not match. After the neural networks have been trained with enough examples of matching records and unmatching records. The neural networks actually figures out what to clue in on that makes records the same or not. Some of the earliest examples of using neural networks for classification purposes was with speech and facial recognition long time ago, back in the 50s, 60s, and 70s. But it wasn't until the 80s when neural networks really came into their own, and then really the 90s when they became commercially viable. And now in the 2000s, we are finally getting them in healthcare. But they've been used in all kinds of examples, such as analyzing sales data or fraud detection, looking for patterns that indicate something nefarious going on. Dynamic pricing, all use neural networks of some form to help determine how to classify something. A short word about clustering, because it's really important to understand this distinction. Most old patient matching systems only work on pairs of records. But that's kind of a problem because many patient records are duplicated more than once. Maybe a patient has trouble with registration because they're hard of hearing, they have behavioral health issues, they're homeless, or they're just not telling the truth. Or more likely, they just have a name that's hard to spell, or language barrier. Any number of reasons could make patients have a lot of medical records all belong to the same patient. And what's great about machine learning, the future of patient matching, is that machine learning is great at clustering. So let's consider this real-world example that illustrates how clustered records help with analysis. This is a real-world data set that shows how many patient records used the same social security number and other demographic identifying information. Now, some social security numbers, all the way to the far left, were shared by a large number of patient records. In one case, 11 patients had the same social security number, but different patients. And another example, there was 9 records that shared the same social security number. Again, different patients. And what this data led us towards was there was some amount of fraud going on in the hospital where a certain subset of otherwise valid social security numbers were being used over and over again to get medical treatment. We would not have known that had we not had clustering techniques available to us. Looking towards the middle of the graph, we can see that there's a certain class of patients that required extra help at registration. And upon inspection, most of these had low-density languages as their native language. These were people that had languages that made it hard for their names to be spelled, and ultimately that created a lot of duplicate records. And there were some homeless people and behavioral health people in this patient cohort too, but the predominant amount of data here was simply hard to spell names. The last cluster of data to the far right are really more typical duplicate errors that you see. Clusters of 3 or clusters of 2 records that share the same social security number, and these were mostly due to errors at registration, typing errors, or really just failure to find the record before a new one was registered. A lot of times this happens at labs, for example. Let's talk more about the potential of machine learning. It replicates how humans solve problems. That's really kind of crazy about it. It understands, or at least it kind of models, how we innately recognize duplicate records upon first glance. When I look at medical records side by side, the answer almost always jumps out at you. Characters are transposed, it's a nickname, the date of birth is off by 1 digit, the next of kin is identical, and there's other indicators that, oh, the street is a little bit off, but it's the same person. And that's what neural networks are really good at, but doing it at scale. Not just 2 records at a time, but the entire MPI at once. The abstract notion of similarity that we just inherently understand, having computer programs do that for us, that's exciting. And machine learning has many other uses in healthcare, especially for clinical situations. It's great at detecting anomalies in images, for example, finding cancerous cells present in an image or not. And it's a great predictor what patients need, what kind of treatments, what illnesses may patients get in the future. And one area that machine learning is doing a lot of work in is in discharge analysis, helping to predict which patients need a little bit extra care at the hospital before they're discharged, so they're not readmitted again in 30 days. That's a big use for machine learning. One of the new approaches that I really like in patient matching, this new name of a class of algorithms that I'm calling soft biometrics. And we discussed earlier that biometric solutions are really expensive because of the hardware, both the implementation and the maintenance of those devices. But the cool thing is, most providers already have biometric data in their MPIs. Patient signatures, for example. And signature matching is a machine learning technique that is done very well today. And if you think about it, HIM professionals that look at duplicate records ultimately make a decision many times by looking at the forms that the patients sign, comparing the signatures. So we do this process, we just do it manually. And software in other industries actually compare signatures now for validation. Banking is a good example. So why doesn't healthcare have it? We can. We should. Something to think about. A near-term solution. The future of patient matching is literally right around the corner. We just have to do it. And we can use sophisticated imaging algorithms to find signatures on the page, extract those signatures, and then build a biometric signature, so to speak, no pun intended, of the signature. Then we can compare those biometric markers of one patient to another to look for similar patients. Just like we do with any other data, like patient names, like social security numbers, except now we're using biometric data, digitized forms of the signatures, to do that comparison. This is a process we should be automating now because it's very powerful, and we'll find a lot of medical duplicate records that other algorithms have not found yet. We will talk about hidden duplicates towards the end of the conversation. Another area of soft biometrics that's particularly interesting and useful is facial recognition. Most providers have scanned copies of photo IDs in their MPIs. And with artificial intelligence and imaging techniques, we can profile the facial geometry and use machine learning to match photos together. And humans do this all the time. When IDs are checked, say for traveling, getting on a plane, visual inspection of the person against the photo is required before the person can proceed forward through security. And if you think about it, those of us who use iPhones, and maybe other phone manufacturers, use facial recognition for the login to the phone. It works amazingly well. This is the near future of patient identification. Soft biometrics from scanned photo IDs. We can match a lot of patient records this way too. Consider that anybody who takes photos typically has a photo album on their phone, on their computer, maybe on the cloud at Google or Amazon or elsewhere. Automatically collect all the photos of specific people and put them into one album. If that kind of computing power is available on your phone, of course we can do this on the big machines we have for our EHRs. Time for photo recognition is now. We should have this today because we have it on our phone and it works really well, and we can protect patients with the data we already have in our MPIs. Now, one of the newest approaches for record linkage and duplicate detection in healthcare is pattern matching. And this technology has been around in other industries for decades. In fact, you use it almost every day when you use Google or any other internet search. Like signature matching and facial recognition, we use advanced mathematical techniques to find patterns in the data that we can then match against other patterns in the system to find duplicates. This works well for demographic data, for clinical data, and even an aggregate of all kinds of information, social determinants, demographics, clinical, and others for population health techniques. This is the future of patient matching because it works so well. Pattern matching is the future of record deduplication because it brings a high level of fault tolerance to matching patient records, unlike we've ever seen before. Recall earlier that we discussed one of the bigger weaknesses of scoring algorithms is because they fail to find patients when the data is not close enough or not exact. In other words, they're not very tolerant of faults in the data. And anyone who has ever studied MPI data knows we have a lot of errors in the MPIs. The misspellings, the wrong punctuation, the nicknames placed in the wrong field, etc. This is what causes duplicate records. AHIMA reports that we have between 8 to 12% duplicate rates on average. That means every time we do a search, we have a 1 out of 12.5 or a 1 out of 8.3 chance, respectively, of finding part of a duplicate record because of those data errors inherent in the MPI database. And that's a big weakness with those deterministic and probabilistic matching algorithms, is how closely each field must match before we can consider it in the score. And if we don't have enough close matches, it falls below that threshold. So we get a lot of false negatives because the data isn't similar enough to be considered a match. The fault tolerance of pattern matching, however, changes that equation because of how the pattern matching works. And it's important because our MPI data has a high level of errors. How pattern matching works is that it converts text to a mathematical model, and for convenience sake, we're displaying as a histogram here. But that mathematical model represents tiny fragments of text that appeared in the medical record data. And this process is quite similar to how internet search works. And the style of pattern matching for internet is directly applicable to finding patient records. The small text snippets are tiny patterns that can be matched. And we do this for every single field that we want to compare, just like with the older algorithms. And once this mathematical profile is built, it uniquely identifies that patient, usually enough to differentiate it from others. If enough of these tiny text fragments match, then we have records that match. We're no longer worried about field by field basis. And this is the foundation as well for modern search. The algorithm breaks down the medical records into the tiny fragments. And those fragments are what give us the fault tolerance. Because we're only matching on small chunks of text that are less likely to have errors than longer chunks of text. It's the fundamental principle of pattern matching for medical records. This creates a very powerful fault-tolerant matching capability that locates patients we might otherwise never find. And lastly, in terms of pattern matching, I really do want to give an honorable mention, if you will, to the universal patient identifier. Now let's be clear, we are a long way from getting a UPI anytime soon, but at least our legislative body is starting to consider removing a restriction for such a number for patients. But let's consider what impact a UPI would have on patient matching. So this is a future technology, not necessarily near term, but a future technology. The entire point of patient matching is to uniquely and positively identify patients. And we've discussed many complicated mathematical models and some solutions that go back a century to solve this same problem. But fundamentally, we're looking for a unique ID per patient, and that's what UPI is all about. If we had a fully implemented UPI, that would solve the vast majority of patient identity problems. Not all of them, but many. We do, however, have proxies for UPIs right now, but they're not used as often as you would hope. So let's discuss. Can you think of any data that's unique or likely to be unique in our MPIs? The trends of social security numbers are dropping for sure. What other data might uniquely identify patients? One thing can be sure, it's definitely not patient names. As we know from our patient search and matching, there's so many names that are similar or so many ways to misspell names that names are not good proxies for uniqueness. We simply can't trust that they're correct. And there's a lot of patient names that are repeated over and over again. My name James, for example. Last name Smith. Last name Garcia. First name Jose. So many names are similar that patient names just don't work for uniqueness. Some names anyway. We talked about social security numbers. For the longest while, they were the de facto medical ID, but we are moving away from that as an industry. AHIMA is recommended against it. The Social Security Administration has never condoned it as a medical ID for anything other than Social Security benefits. So the trend of using Social Security numbers is dropping, and because ID theft is high, American society has become even more cautious about using their social in places where they don't have to. But that said, Social Security number still is very effective for resolving duplicates. But there's other data that's similar. How about cell phones and emails? They're very common. They're almost always for individuals. Sometimes they're shared, but mostly not. And there's almost 8 billion potential numbers just in the USA that could be uniquely identified with the person, perhaps. And an infinite number of emails. We're never going to run out of emails, unique emails for patients, assuming they have one. Now, patients can and do change emails and can and do change cell phone numbers. I understand that. That's why we should maintain a historical record of all patient changes, so we can look at that historical data, phone numbers and email, to see if a patient matches any of what they're giving us. That historical information tracking is also good for overlay detection. We'll talk about that more at the end. Now, admittedly, cell phones and emails are not perfect proxies for UPIs, but they are the best data we can get that's going to uniquely identify a patient, with the exception of a social security number. But emails and cell phone numbers aren't hijacked as much, so they might even be better than social security numbers in other ways. We're going to finish our conversation about the methodologies for patient matching and talk about a much bigger issue that's closely related to algorithms for matching patients. Despite whatever an EHR vendor tells you, or an EMPI vendor tells you, or a patient matching software vendor ever tells you, no one algorithm is the best for every single type of duplicate. There's no one single best way or right way to do it. Every matching approach has a limitation, a blind spot about the types of matches they can find the easiest. And this whole presentation was about the pros and cons of the current and future matching techniques, because they look at different data characteristics, names that sound alike, social security numbers or other demographic data that matches or not, records, missing data, names look alike, people look alike, signatures are similar, and so forth. And every single approach will find a different kind of matching record. And what we also know and recognize is that very few organizations use multiple approaches to match records. They typically use one, maybe two, when in reality they should be using 3 or 4. And given the state of duplicate records in our industry and the number of data errors, the root causes of duplicates, every organization needs to try harder to clean their data. We have more duplicates than we know, and I call them hidden duplicates. Doing social security number matches will not find nicknames that relate to given names and match those records. And looking for social security numbers to find patients to have a new, say, married name isn't going to help us either, especially if the patient is not given the socials anymore. Another reason for hidden duplicates is because of algorithm tuning. These thresholds really do matter for scoring algorithms, and they also change over time as patient demographics change, as MPIs are merged with other MPIs. It's best practice to look at your thresholds about once a year and retune your system to make sure you're catching all the duplicates you should. But most providers and IT shops sort of think of this as a set it and forget it threshold. But you always need to have a tune-up for your car. You always need to have your heaters and air conditions in your home checked and maintained. And the same thing is true for your matching engines. Those thresholds need to be adjusted. We're going to touch briefly on this topic of error prevention because this is an entire hour-long seminar in and of itself. But using the modern pattern matching techniques, there are 3 interesting ways that we can prevent errors from getting into your MPI in the first place. The first is data cleaning. Using pattern matching in your MPIs will quickly identify the kinds of errors that you're having on a recurring basis. And just like we have cues for cleaning duplicate records, we should also have the same kind of cues for cleaning the data elements that are not accurate, like street names that are misspelled. These are the kind of things pattern matching solutions can find. One of the coolest things I've ever seen in industry was the use of a matching software engine as a bumper guard, as the customer called it, bumper guard around their EHR. I also call this a 2-stage registration. But what we're doing in both cases, we're using the power of a matching engine, whether it's a current technology solution like the customer with the bumper guards, or a pattern matching solution for 2-stage registration. So what we're doing is we're using the power of matching in place where a search function goes. So we are replacing the EHR's search function with a much more powerful matching engine. So in the bumper guards example, every time a customer's registration staff did a search, that search was then piped over to the matching engine just to make sure there's not a patient that exists with that same exact demographics before they were allowed to proceed to register the patient. And 2-stage registration works the same way. And whether we do it for all the registration points or just a few that are problematic, every time there's an attempt to store a brand new record in MPI, the matching engine grabs it and confirms that there are no other patients that are similar. And this is why we use the pattern matching in this technique, because we're looking for similar records that are close enough to make us double check the entry, not exact. And lastly, we'll talk about patient search. The MPI bumper guards and the 2-stage registration were really an attempt to replace or augment the EHR search function. But in reality, EHR searches should be replaced by technology, not just kind of augmented. If we had pattern matching capabilities at the front end of any EHR, and we truly had internet-like search flexibility, where it understands the context of the search and it's fault tolerant to work even with our errors typing in the search fields and with the errors back in the MPI itself, a powerful pattern matching algorithm used in a patient search functionality will prevent a lot of errors from occurring. The duplicate record never gets a chance to be entered into the system. The patient search function was powerful enough to find what you meant to find rather than what the data matches or doesn't match. 3 very powerful ideas that we can use with pattern matching to prevent errors. And we'll close out the presentation with a preview of other uses of modern matching technologies. We just discussed patient search, but related. Matching opioid usage patterns across state lines is an area that is in dire need of very flexible, fault-tolerant patient matching. It's well known that data between different providers has a very low probability of matching, and that holds true for the opioid databases that have patient information in them as well. Different state laws, different data collection, different normalization processes lead to a very difficult ability to match patients in different databases. The same is true for the anti-information blocking regulation that is now going into effect. Using advanced pattern matching as your search on the front end for patient requests from external providers has a much better chance working with high fault tolerant systems than it does with exact matches. For the same reason of the opioid usage matching. Different providers enter data in different ways, and that causes many problems in patient matching. We mentioned population health earlier, and with machine learning and fault tolerance of pattern matching together, anyone who wants to analyze a population for a variety of factors can use that technology to blindly cluster the data. For example, you can bring in information from the patient's clinical data, social determinant data, and then demographic data, and create a brand new profile of a patient that you can then cluster using machine learning to see which patient groups belong together. You can spot the similarities for the members of that group. Great tool for population health. Clinical documentation error prevention is really cool because there's a big problem with copy and pasted notes in patient records. And we can use the similarity capabilities, pattern matching, to find that kind of copy and paste language that is shared between patient records. It's exactly like a duplicate record. We're looking for patterns that match in clinical data, not demographic data. And the same thing is true looking for templated language in the clinical notes. And one of my favorite topics of all time is overlay prevention. Nobody talks about overlay prevention and detection because there are no systems that do it yet. This is a true near-term solution that's coming. And it's only possible because of the ability to detect patterns in the data. With a fault-tolerant search, we would encourage users to type in more information as much as possible to weed out the records that don't apply and to narrow in specifically on the record that you're trying to match. Even with errors, it still works. So I always say with search, go ahead and type everything you want, everything you can, because that is the first step to eliminating overlay records. So in summary, to understand the future of patient matching, we had to go back and look at history as well as the present to know what we need for the future. And that future is just around the corner. Patient matching technologies have evolved over time. And this presentation went through as much as we could. We focused towards the end on future solutions that really will make a substantial change in the patient matching industry. We borrowed ideas from other industries, and we explored how patient works in the abstract. And we did this so we could learn the pitfalls of all the different techniques. We learned the applicability of common matching approaches, where they're best used, and how to understand what kind of duplicates do they find. That helped us to understand newer advances in healthcare IT for patient matching. And until recently, the most current new thing came from the 1960s. But the advances over the past 3 to 4, 5 years have made a substantial improvement in healthcare's ability to find duplicate patients. And then lastly, we just closed on how to prevent errors using the modern matching techniques. Not much time to go into the details, but just a glimpse of what's possible in the future. Future being tomorrow, not a decade from now. And then of course, there's all kind of ways we can apply these pattern matching technologies to other areas in healthcare that we just touched on. But particularly overlay protection is something I'm going to really focus on this year. Whew. Well, we made it to the end, and everyone's still alive, I hope. Take your balls. I hope you learned a lot from the presentation. My emails and contacts are available in the presentation, so please feel free to reach out to me. There's a lot of important data that's in the video, and I hope some of it was useful for your organization. There's a lot of work we have to do in industry, and hopefully next year we'll be talking about some other interesting topics that are related to improving patient matching and patient search. Have a great rest of the conference, and thank you so much for attending my video. Bye-bye.